High above the Earth, beyond the familiar troposphere and stratosphere, lies a realm of charged particles and electromagnetic wonders, the ionosphere. This layer, stretching from around 50 to 600 miles above us, is where the atmosphere meets the raw energy of the sun. Here, solar radiation transforms atoms into ions and electrons, creating an electrically charged region that plays a vital role in our technological world. The ionosphere is not a single, uniform layer. Instead, it's structured into distinct layers, D, E, and F, each with its own characteristics. The D layer, closest to Earth, is present only during the day, while the E and F layers persist both day and night. The F layer, further subdivided into F1 and F2, is particularly crucial for long-distance radio communication. This dynamic region, constantly bombarded by solar radiation and influenced by Earth's magnetic field, is a realm of ongoing scientific fascination. Understanding the ionosphere is key to unraveling the mysteries of space weather, improving communication systems, and ensuring the safety of satellites and astronauts. The ionosphere's impact extends far beyond its ethereal realm, directly affecting our everyday lives in ways we often take for granted. From radio broadcasts to GPS navigation, this invisible layer plays a silent but crucial role in our technologically interconnected world. One of the most remarkable properties of the ionosphere is its ability to reflect radio waves. This phenomenon, discovered in the early 20th century, revolutionized long-distance communication and laid the foundation for our modern wireless world. When a radio wave transmitted from Earth reaches the ionosphere, it interacts with the charged particles present there. Depending on the wave's frequency and the ionosphere's electron density, the wave can be refracted or bent back towards Earth. This reflection allows radio signals to travel beyond the horizon, enabling communication over vast distances. The different layers of the ionosphere affect radio waves differently. The D layer, present during the day, absorbs lower-frequency radio waves, while the E and F layers reflect higher frequencies. This selective reflection is why AM radio broadcasts, using lower frequencies, can travel longer distances at night when the D layer disappears. The ionosphere's ability to reflect radio waves is not constant and varies depending on the time of day, solar activity, and other factors. Understanding these variations is crucial for maintaining reliable radio communication, especially for aviation and maritime navigation. As the sun rises and bathes the Earth in its light, the ionosphere undergoes a dramatic transformation. Solar radiation, particularly ultraviolet and X-rays, bombard the upper atmosphere, stripping electrons from atoms and creating a dense layer of ions and electrons. This ionization process is most intense in the D region, which forms only during the day. The D layer, though relatively thin, plays a crucial role in absorbing lower-frequency radio waves, preventing them from reaching higher layers. This absorption is why AM radio stations often switch to lower power or different frequencies during the day to maintain coverage. Higher in the ionosphere, the E and F layers also become more ionized and denser during the day. This increased ionization allows them to reflect higher frequency radio waves, enabling long-distance communication on shortwave bands. The daytime ionosphere, energized by the sun, is a dynamic and constantly changing environment. Understanding these variations is essential for predicting radio wave propagation and ensuring reliable communication. As the sun sets and darkness envelops the Earth, the ionosphere undergoes another transformation, this time in reverse. With the absence of solar radiation, the ionization process slows down, and the ionosphere begins to recombine. The D layer, no longer sustained by solar energy, disappears entirely, allowing lower frequency radio waves to pass through to the higher layers. This is why AM radio stations can often be heard at much greater distances at night. The E and F layers, though still present, become less dense and less ionized. This reduction in electron density affects their ability to reflect radio waves, particularly higher frequencies. As a result, long-distance communication on shortwave bands becomes more challenging, and radio operators may need to adjust frequencies to maintain contact. The nighttime ionosphere, though less active than its daytime counterpart, still plays a vital role in radio communication, particularly for long-distance broadcasts and maritime navigation. Section 5. Ionospheric impacts on aviation. The ionosphere's ability to reflect radio waves has been a boon for aviation, enabling long-distance communication between aircraft and ground stations, especially over oceans where ground-based radio signals cannot reach. However, the ionosphere is not a static reflector, but a dynamic and ever-changing environment. Its variability can significantly impact aviation communication, causing signal fading, distortion, and even complete blackouts. Solar flares and other space weather events can disrupt the ionosphere, creating sudden changes in electron density that can interrupt communication links. These disruptions can pose significant challenges for pilots, especially during critical phases of flight. To mitigate these challenges, modern aviation relies on a combination of technologies, including satellite communication systems and advanced ionospheric monitoring and prediction models to ensure reliable and safe air travel. Section 6. The Ionosphere and Space Exploration. The ionosphere, the boundary between Earth's atmosphere and space, poses both challenges and opportunities for space exploration. As spacecraft travel through this region, they encounter charged particles that can interfere with communication systems and onboard electronics. The ionosphere's impact on radio signals can disrupt communication between spacecraft and ground stations, requiring engineers to design robust communication systems and employ strategies to minimize signal loss or distortion. Moreover, the charged particles in the ionosphere can build up on spacecraft surfaces, leading to a phenomenon known as spacecraft charging. This charging can disrupt sensitive instruments and even damage onboard electronics. Despite these challenges, the ionosphere also provides opportunities for scientific study. By observing how radio signals from distant stars and galaxies pass through the ionosphere, scientists can learn about its composition, density, and dynamics. Section 7. Space weather and the ionosphere. The ionosphere is not isolated from the Sun's activity. Just as solar flares and coronal mass ejections can disrupt power grids and satellite operations on Earth, they can also dramatically impact the ionosphere. These space weather events release vast amounts of energy and charged particles that interact with Earth's magnetic field and the ionosphere, creating geomagnetic storms. These storms can enhance ionization, particularly in the polar regions, leading to auroras and other spectacular visual displays. However, these storms can also have disruptive effects, causing radio blackouts, disrupting GPS navigation, and even damaging satellites. Understanding and predicting space weather events and their impact on the ionosphere is crucial for mitigating these risks. Space weather forecasting and ionospheric monitoring are essential for protecting our technological infrastructure and ensuring the safety of astronauts and spacecraft in orbit. Section 8. Studying the ionosphere. Scientists employ various techniques to study the ionosphere, ranging from ground-based observations to sophisticated satellite missions. Ground-based instruments, such as ionosondes, transmit radio waves vertically into the atmosphere and measure the time it takes for the signals to be reflected back, providing information about the ionosphere's height and electron density. Satellite missions, such as NASA's GOLD, which stands for Global Scale Observations of the Limb and Disk, and ICON, the Ionospheric Connection Explorer, provide a global perspective of the ionosphere, measuring its composition, temperature, and dynamics. These missions help scientists understand the complex interplay between the ionosphere, the Sun, and Earth's magnetic field. By studying the ionosphere, scientists hope to unravel its mysteries, improve space weather forecasting, enhance communication and navigation systems, and ensure the safety of our technological assets in space. Section 9. Conclusion: the ionosphere's enduring significance. The ionosphere, an often overlooked region of our atmosphere, plays a vital and multifaceted role in our technological world. From reflecting radio waves for long-distance communication, to interacting with space weather, and influencing satellite operations, this dynamic layer has a profound impact on our lives. As we become increasingly reliant on space-based technologies for communication, navigation, and Earth observation, understanding and monitoring the ionosphere becomes ever more critical. By continuing to study this complex and dynamic region, we can mitigate the risks posed by space weather, enhance the reliability of our technological systems, and ensure a sustainable future for space exploration. The ionosphere, a silent guardian of our technological age, deserves our attention and respect as we venture further into the cosmos.